Welcome to INEN 675 Design Experiments. In Lecture 1, we're going to talk about the introduction of design experiments. Here is the agenda. We're going to look at why is this trip necessary, what are the goals of the course. We're going to talk briefly about the history and discuss some basic principles and terminology and the strategy of experimentation, and discuss the guidelines for planning, conducting, and analyzing experiments. So why is this trip necessary? Design experiments are very important in planning and conducting experiments and analyzing the resulting data so that valid and objective conclusions are obtained. Experimentation is a very vital part of the scientific or engineering method to explore a particular process or system. For example, an engineer is interested in studying the effect of two different hardening processes on an aluminum alloy. The goal here is to decide which solution produces the maximum hardness for this particular alloy. The engineer decides to subject a number of alloy specimens to each medium and measure the hardness of the specimens after quenching. The average hardness of the specimens treated in each solution will be used to determine which solution is better. In this experiment, there are some very important issues that need to be addressed. For example, are these two solutions the only media of potential interest? Are there any other factors that might affect hardness that should be investigated or controlled in this experiment? How many coupons of alloy should be tested in each solution? How should the test coupons be assigned to the solutions? And in what order should the data be collected? What method of data analysis should be used? What difference in average observed hardness between the two quenching media will be considered important? An experiment is a test or a series of tests in which changes are made to the input variable of a process or system as that we may observe and identify the reasons for changes that may be observed in the output response. So we have input variable, we have output variable, and we have controllable factors and uncontrollable factors for a process. A process is a combination of operations, people, machines, methods, and other resources. Engineering experiments can be used for process characterization, optimization, evaluation of material properties, product design and development, component and system tolerance determination, and they are used to reduce time, to design, to improve performance, to improve reliability, to achieve product and process robustness, and for evaluation of materials, design alternatives, setting component and system tolerances, etc. It's important to remember all experiments are design experiments. It just some are very poorly designed, some are well designed. The reason we're studying this course is we wanted to have well-designed experiments. The objectives of experiments: which variables are most influential on the response variable, where to set x's so that y is almost always near the desired nominal value, where to set x's so that the variability in y is small, where to set x's so that the effects of the uncontrollable variable z's are minimized. Experiments can be classified as variable screening, treatment comparison, response surface exploration, system optimization, and system robustness. Let's look at an example. A flow solder machine is used in the manufacturing process for printed circuit boards. The machine cleans the boards in the flux, preheats the boards, and then moves them along a conveyor through a wave of molten solder. This solder process makes the electrical and mechanical connectors for the leaded components on the board. The process currently operates around the 1% defective level, and engineering plans to use a design experiment to determine which machine parameters are most influential in the occurrence of solder defects, which adjustments should be made to those variables to reduce the solder defects. So here's the process. In addition to these controllable factors, several other factors cannot be easily controlled during routine manufacturing, although they could be controlled for the purpose of an experiment. Those include the thickness of the principal board, types of components used on the board, layout of the components on the board, and operator product rate. This screening or characterization experiment can be used to identify the critical process factors. How much does the response variable change when each factor is changed? Do the factors interact? Determine the direction of adjustment for these factors to reduce the number of defects per unit. So those could be the goals for this particular experiment. Now let's look at the 4 eras in the history of design experiment. The first era is the agricultural era between 1918 to 1940. The most important person in this era is Fisher and his co-workers. They systematically introduced statistical thinking and principles into design experiments. Their findings have a profound impact on agricultural science. They introduced the 3 fundamental principles of design experiments, and they introduced the factorial design and analysis of variance. Their focus is on treatment comparison. The second era is the first industrial era, between 1951 to late 1970s. The important people are Box and Wilson. They introduced the response surface methodology, central composite design, and optimal designs. Their applications are in the chemical and process industries. The focus is on process modeling and optimization. The third era is the second industrial era from late 1970s to 1990. Quality improvement initiatives in many companies, Taguchi and a robust parameter design, process robustness. Although Taguchi's engineering concepts and objectives are well-founded, there were substantial problems with his experimental strategy and methods of data analysis. Later in the semester, we will talk about Taguchi's robust design. The last era is the modern era. It's popular outside of statistics and an indispensable tool in many scientific and engineering researchers. There are new challenges. Large and complex experiments, for example, screening design in pharmaceutical industry, experimental design in biotechnology, and computer experiments. There are efficient ways to model complex systems based on computer simulation, for example, weather and climate model. The 3 basic principles of design experiments. The first is randomization. Allocation of units to the treatments need to be randomized. Running the trials in an experiment should be in the random order. It protects against latent variables and subjective biases. Ensures the validity of experimental error estimation. Ensure the validity of statistical inferences. For example, a lot of times you need to have independent identically distributed data. The randomization is very important to ensure that. Complete randomization makes it possible to derive and perform randomization distribution and randomization test. Notion of balancing out effects of overlooking variables needs randomization. Second principle is replication. Each treatment is applied to a number of units that are representative of the population. Replication enables the estimation of experimental error. If you only have a single replicate, you will not be able to estimate the experimental error. Replication also increases the power to detect the important effects. The larger the sample size is, the more powerful your experiment is in detecting certain effects. There is a difference between replication versus repeated measures. We will talk about this later. The third principle is blocking. A block refers to a group of homogeneous units. In other words, units within a block should be very, very similar. It can be used to reduce or eliminate the variability transmitted from nuisance factors. Now, within block variation need to be much smaller than the between block variation. There is trade-off between variation and the degree of freedoms. When we discuss the randomized block design, we will talk more detail about this. Just remember, we should block what we can and randomize what we cannot. Let's take a look at the source of variation factors. A source of variation is anything that could cause an observation to have a different numerical value from another observation. We all know when we make observations, not each time you might get a different value, and why the values are different. There are many sources of variation. The major sources of variation can be divided into the following two types. Treatment factors. These are the factors of particular interest to the experimenter, or nuisance factor. Those are the factors that are not of particular interest to us. Treatment means a level of a treatment factor in a single factor experiment, or a treatment combination when there are two or more treatment factors. So treatment in a single factor experiment, let's say the single factor is temperature, there are two levels, then each treatment could mean a level of the temperature. Now, suppose you have a two-factor experiments, temperature as well as type of material, then treatment here refers to the combination of temperature level and the type of material. If the levels of treatment factor are quantitative, then they are usually chosen to be equally spaced. Flowchart and the cause and effect diagram are very helpful for identifying potential factors. For instance, a paperboard manufacturing process involves raw materials from suppliers, a chemical process to make a slurry, which is passed through a mechanical process to produce the pulp. A flowchart of the process or system is helpful to see whether the factors arise in the multi-stage process. So from here, we can fairly easily to see what affects this whole process. And a cause and effect diagram can help identify the factors that affect the product quality of an injection molding process in this example. Experimental units. Experimental units are the material to which the levels of the treatment factor are applied. For example, in agriculture, those could be individual plots of land. In medicine, these could be human or animal subjects. In industry, this might be batches of raw material, factory workers, etc. Experimental units should be representative of the material and conditions to which the conclusions of the experiment will be applied. Nuisance factors. Blocking factors induce a group of relatively homogeneous experimental units or conditions. For example, plots of land or times of day that are close together are more likely to be similar than those far apart. Subjects with similar characteristics are more likely to respond in similar ways to a drug than those with different characteristics. Observations made in the same factory are more likely to be similar than observations made in different ones. Covariate usually means a property of the experimental units and can be measured before the experiment takes place. For example, the blood pressure of a patient in a medical experiment, the IQ of a pupil in an educational experiment, the acidity of a plot of land in an agricultural experiment. assignment rule. The assignment rule or the experimental design specifies which experiment units are to be observed under which treatments. The actual assignment of experimental units to treatments should be done at random, subject to restrictions imposed by the chosen design. Later on, we're going to introduce a checklist for planning experiment. All steps in the checklist should be considered carefully before actually conducting experiments. A well-planned experiment usually leads to a great saving of time and funding. How to use statistical experimentation. We need to use your non-statistical knowledge of the problem and to keep the design and analysis as simple as possible. Experiments are usually iterative. Recognize the difference between practical and statistical significance. Throughout the semester, we're going to use SAS to solve problems. SAS, or Statistical Analysis System, is an integrated system that can perform data access, data management, data analysis, data presentation. Take a look at SAS. SAS environment has editor window, log window, output window. The analogy between SAS and articles, the SAS program is just like article, and data steps or proc steps just like paragraphs, and the statements just like sentences. Here is a sample SAS code. We will have a chance to talk this more and use see some more examples. Some basics of SAS programming. A SAS dataset contains the information we want to analyze. Each row corresponds to an observation. Each column corresponds to a variable. A SAS program usually contains the following two parts. Data steps are used to manipulate data sets. Proc steps are used to analyze data sets to produce statistics tables, plots, etc. SAS steps begin with either of the following: a data statement or a proc statement. SAS detects the end of a step when it encounters one of the following: a run statement, a quit statement, or the beginning of another step. Syntax rules for SAS statements. Each SAS step is comprised of some statements. It usually begins with a keyword. Each statement ends in a semicolon. Statements are free format. One or more blanks can be used to separate words. They can begin and end in any column. A single statement can span multiple lines. Several statements can be on the same line, and you can comment your code. To submit your program to run, by clicking on the icon in the toolbar, you can save your program every time. You're encouraged to save your program each time before you submit it to run. A run statement tells SAS to process the previous piece of program that you wrote. If there is no run statement, SAS will not process anything when you submit your program. The data line statements should be placed after the input statement and towards the end of the data step. A semicolon at the beginning of a new line is required to indicate the end of data lines. There are two major types of variables: a character variable indicated by a $sign after the character variable, and numerical variable can only contain numeric values. SAS names have these characteristics. It starts with a letter or underscore. Subsequent characters can be letters, underscores, or numbers. No blanks or special characters are allowed. No more than 32 characters in length. It can be a combination of uppercase, lowercase, or mixed case. You can create dataset from external files. the keyword would be in file. The in file statement should be placed immediately after the data statement and before the input statement. In data steps, you can define new variables, create new data sets from existing data sets, and so on and so forth. And you can use if-then statement. Proc print is used to show contents of a data set. It's strongly recommended that you always include data option in proc statement, especially when you are working with several data sets simultaneously. Proc sort sorts the observation of the data set by some variables in either ascending or descending order. By default, it will be sorted as ascending. If you want to sort by descending, you need to specify the keyword descending. Proc means calculate simple univariate descriptive statistics for numeric variables. By default, I'll put the number of observations, mean, standard deviation, minimum, and maximum. Common syntax errors include misspelled keywords, missing or invalid punctuation, invalid options. To find out syntax errors, in the editor window, pay attention to the color of the text, which may help you identify syntax errors. Check the log window for any errors. Here is a sample code with errors. Some of the problems here, for instance, the variable toSubject starts with a number, which is not valid, and the proc print statement does not have a semicolon at the end of it. Now let's look at the strategy of experimentation. The first strategy of design experiment is called best guess experiments. It's used a lot, and it's more successful than you might suspect, but there are some disadvantages. Best guess approach works reasonably well at times because the engineer often has a great deal of technical or theoretical knowledge of the system they are studying at, as well as considerable practical experience. However, there are at least two disadvantages for the best guess approach. First, suppose the initial best guess does not produce the desired results. Now, the engineer has to take another guess at the correct combination of factor levels. This could continue for a long time without guarantee of success. Second, suppose the initial best guess produces an acceptable result. Now, the engineer is tempted to stop testing, although there is no guarantee that the best solution has been found. In addition, it is often difficult to explain to others how the optimal combination of factors are arrived at, to quantify how much each factor contributes to the responses, or to obtain a prediction equation. The second strategy is called one factor at a time OFAT experiment. Sometimes this approach is associated with the scientific or engineering method. It's actually widely used in mechanical and civil engineering. It is devastated by interaction and also is very inefficient. The OFAT method is considered as the standard systematic and accepted method of scientific experimentation. This method consists of selecting a starting point or baseline set of levels for each factor, then successively varying each factor over its range with the other factors held constant at the baseline level. After all tests are performed, a series of graphs are usually constructed showing how the response variables are affected by varying each factor with all other factors held constant. The major disadvantage of the OFAT strategy is that it fails to consider any possible of interaction between the factors. An interaction is the failure of the one factor to produce the same effect on the response at different levels of another factor. Interactions between factors are very common in engineering experiments as in everyday life, and if they occur, the OFAT method will produce poor and sometimes disastrous results. Many people, including experienced researchers, do not recognize this, or if they did, do not know how to quantify it. Consequently, the OFAT method is still frequently used in practice. An example of an interaction effect from our daily life is drinking alcohol when taking certain prescription or non-prescription drug. When the drug and alcohol are taken together, it might be fatal. Yet, when taken separately, it may be quite harmless, or at least has no serious consequences. One can see that the only way that the interaction effect can be discovered is to take the two substances together. A better strategy is to use statistical design experiments. This is based on Fisher's factorial concept. Instead of varying one factor at a time, the factorial approach says that one should vary all factors simultaneously to deal with interactions and maximize efficiency, and do the experiments in random order to maximize accuracy and reduce the chance of wrong conclusions. In factorial design, all possible combinations of factor levels are tested. In a textbook, the author provided an example of a golf experiment. Factors include type of driver, type of ball, walking versus riding, type of beverage, time of round, weather, type of golf spike, etc., etc. A two-factor factorial experiment could have two factors, type of driver, type of ball. Each has two levels. And at each treatment combination, two observations or two scores were obtained. Figure BC provides how to calculate the effect for a single factor, and figure D provides the interaction effect. Factorial design can be done with several factors, 3, 4, or even more. And sometimes we also can conduct a fractional factorial design. More details will be offered when we introduce factorial design later in the semester. In the textbook, the author provided some guidelines for planning, conducting, and analyzing an experiment. First, recognition and statement of problem. Second, choice of factors, levels, and ranges. Third, selection of the response variables. Fourth, choice of design. Fifth, conducting the experiment. Sixth, conducting statistical analysis. Finally, draw conclusions and provide recommendations. Here is the checklist for planning experiment. Define the objective of the experiment. Identify all sources of variation, including treatment factors and their levels. Experimental units, nuisance factors. Choose a rule for assigning the experimental units to the treatments. Specify the measurements to be made, the experimental procedure, and the anticipated difficulties. Run a pilot study. Specify the model. Outline the analysis. Calculate the number of observations that need to be taken. Review the decisions. Revise if necessary.